The universe is going to hell in a handbasket, predicting the spontaneity of a reaction using entropy. Part 2. In class the other day, the lecture was organized around an initial question, which was, what makes things in the natural world happen? So as part of that lecture, we learned that processes that happen on their own without outside ongoing intervention are called spontaneous. We learned that the property that determines whether or not something happens in the natural world is called entropy, which is symbolized by the variable S, which, by the way, is a measure of the disorder of a system. We further became aware of the fact that it is not energy, or enthalpy in this case, that determines whether or not something happens. So it's not delta H, being uphill or downhill, that decides whether a reaction happens automatically. So in other words, reactions do not always go downhill in terms of their heat. Now remember, in class we said that reactions that go downhill are those that are exothermic. We said, but not all reactions that are spontaneous are necessarily downhill or exothermic. Okay, so then we said, well, what law governs this process and how do we use this law to make predictions? We said it wasn't the first law of thermodynamics that determines whether a reaction is spontaneous, but the second law, which says that reactions that increase the entropy of the universe are spontaneous. Okay, so we're going to pick up here and we're going to start talking about how to determine the entropy of the universe, which sounds like a large task. So we're going to start simple. Instead of thinking about the entire universe, we're going to break the universe down into the system and the surroundings, where the system is the actual chemical reaction, just the reagents and products, nothing else, it's not the solvent that the reaction is dissolved in, just the reactants and products, and then everything else, which is the surroundings. Because remember, the system plus the surroundings is equal to the universe. So first off, the system, or the reaction, remember that a reaction is made of individual compounds or molecules, so reactants and products. So we're first going to examine how to determine the entropy of individual substances. And then we're going to use the entropies of those individual substances to figure out the change for a particular reaction. So we'll actually be able to figure out the entropy change, or the delta S, for a reaction. And we can do this two ways. We can do this qualitatively, so we can estimate what the sign for delta S is. And we can do it quantitatively, which means we can actually calculate a numerical value for delta S. And then we'll look at delta S for the surroundings. Okay, so once we know those two things, we can put it all together and hopefully look at the universe. All right, so first, the entropy of individual substances. So it's important to realize that an element has entropy. You might remember that elements don't have a value for delta H if they're in their standard state. So like oxygen gas doesn't take any energy to form from itself. Okay. Entropy of individual substances, though, is different. They actually have entropy, and I like to compare this with a famous cartoon strip, or you're probably more familiar with this in terms of television specials that have been on, and that's the Peanuts. So I like to think of the entropy of the characters in this cartoon. Okay, so who's the most organized character of all? Of course, Lucy. Okay, so Lucy has very low entropy because she's super organized. And then who's the most disorganized, entropic character? Of course, Pigpen. All right, and so we can think of each of these individual characters as having their own entropy in the same way that we think of individual compounds or molecules having entropy. having inherent disorder. Okay, so this is called the absolute entropy. Unlike enthalpy, just H, S can be determined directly. So you notice how we always measure delta H. We never talk about just H. We can talk about just S. Okay, so we call S under standard conditions S naught. Okay, so that little degree sign is really a 0, and so we call it naught, which is a sort of British way of saying 0. And standard conditions, of course, are 25 degrees Celsius and 1 atmosphere pressure. So when we measure the entropy of an individual substance under standard conditions, it's called S naught, or the standard entropy. Okay, so we can come up with a value, a numerical value for the standard entropy. Once again, remembering that this is how disorderly a particular substance actually is. Okay, so what are some factors that you think might impact the absolute entropy of a compound? So temperature, complexity of the compound, the state of matter, and the molar mass. Decide what you believe the answer is. Okay, so if you said D, all of the above, you are actually correct. Temperature, okay, that makes sense to most people. They say, well, if the substance is at a higher temperature, that means that the molecules are moving more quickly, they're going to be more disorganized. Okay, so that makes sense. The higher the temperature, the higher the entropy. Complexity of a compound. The more complicated a compound is, the more complicated the bonding pattern, okay, the more entropic it's going to be. Okay, state of matter. So this is, of course, referring to solid versus liquid versus gas. So what do you think the most disorganized state of matter is? So if you're saying gas, you're on the right path, right? So that makes sense. Now the one that is a little confusing at first glance is the molar mass. So remember, molar mass is the mass of 1 mole of a compound or element or molecule or whatever. So why do you think molar mass might actually impact the entropy? Well, it turns out that the higher the molar mass, the more protons, neutrons, and electrons a particular element has. And protons and neutrons, they don't give the molecule much entropy because they're rather stationary in the middle of the atom. However, remember that electrons can move all over the place. They can jump between energy levels, and they are, in a sense, moving around the nucleus. Really, they're a wave. Okay, so there's a lot of movement with electrons. And so the more electrons a molecule has or an atom has, the more disorder it has, because electrons are inherently disorderly. Okay, and so that's why molar mass is important in determining the entropy of a compound. Okay, so let's look at some ways to qualitatively then compare substances to determine S naught. So we're going to decide who has a higher or lower absolute entropy, which is this value here. So if you have the same, so this is sort of like a set of instructions. If you have the same substance, but it's in different phases. So say, for example, you have a particular substance like carbon, and it's in 3 different phases. The carbon gas will have greater entropy. So gas has greater entropy than liquid, than the solid. And remember, here we're comparing the same thing, but just in different phases. So that's the first thing you can look at. Let's say that instead of having the same substance in different phases, you have different substances all in the same state of matter. Remember, phase and state are synonymous. So in this case, you look at molecular complexity to determine the entropy. So in other words, which one is more complicated? For example, if you had gaseous methane versus ethane. Now you might be thinking, I don't know what methane and ethane are. Methane is a 1-carbon organic compound, so it's CH4, and ethane is a 2-carbon organic compound, so it's CH3CH3. And so you might be thinking, well, CH3CH3 sounds more complicated than CH4, and so here's their structures. Indeed, you would be right. Okay, so ethane has more entropy, okay, because they're both gases. Both methane and ethane are in the same phase, but ethane's more complicated. Now, sometimes those first two criteria don't give you enough information, in which case you need to look at one more criteria. If you have different substances, they're different things, but they're both in the same state of matter, and they're equally complex, then you have to look at the molar mass. So for example, we could look at helium gas versus neon gas. Now I don't have a periodic table up on the screen, but you hopefully recognize those as being members of the noble gas family. And you might even remember that helium is above neon. So what that means, of course, is that helium has a lower molar mass than neon does. Okay, but before we even talk about that, helium and neon are in the same phase. They're gases, and they have the same complexity because they're each composed of one atom. Okay, neither one is a molecule. They don't have different complexity that way. And so then, and only then, you look at molar mass. And so, of course, you're probably saying by this point, neon will have the higher entropy of the two. Okay, so this is just a quick and simple process that you can go through if you're given a list of molecules and are asked to decide which has the higher or lower entropy. Okay, so let's do some practice with that. Which substance has the highest entropy here? Go ahead and buzz in your answer. So if you chose B, N2 gas, you are correct. All three are the same substance, but the gas has the highest entropy. Gas has more movement and therefore more disorder. Okay, for this one, which substance has the highest entropy? Okay, so hopefully you chose A. If you look at all three choices, they're all solids. So that does not decide for us. So then the next criteria is complexity. And C6H12O6, or glucose, is more complex than either of the other two molecules. This one's benzene, and this one's formaldehyde. Okay, and so this guy here has the highest entropy. So good if you chose A. All right, one more. Okay, which of these has the highest entropy? Okay, so this one's a little trickier. So the first thing we can look at is we can note that we have a gas, a solid, a gas, a solid. So immediately we can cross out the two solids because solids have less disorder than gases. Okay, so gases are the most disorderly. It's kind of weird because you have to think about disorder or messiness as being a good thing, right? So we want disorder, we want entropy. So the CO2 and the SO2 are our finalists. And so if we think about it, they're both in the same state of matter and they both have the same complexity because it's CO2 and SO2. So now you must look at molar mass to decide. And since carbon has a lower molar mass, just the C part of this molecule, has a lower molar mass than sulfur, if you look at the periodic table, therefore sulfur dioxide will, choice C is the correct answer. It has the highest entropy. Okay, so that's a basic idea of how you decide the entropy. However, we also are going to need to be able to predict the entropy change of reactions or physical changes like melting and boiling and that kind of thing. All right, and so this will be the entropy change of the system. So one thing you should be aware of is when you see entropy change or like delta S system, that's sort of the same thing as delta S reaction, okay, because a reaction is a type of system. Okay, so those two subscripts are used interchangeably. Alrighty, so how do you predict these? One substance going to another, or several substances becoming several other substances. Okay, so this is doing it qualitatively. So here we're just going to predict whether delta S is plus or minus by looking at the entropies of the materials you start with, the reactants, and the products. So in our previous example, we're going from Lucy to Pigpen, and so the entropy is increasing, right? So the change in entropy must be what? Would it be positive or negative? Well, Pigpen's a lot more entropic than Lucy, right? So entropy is going up, and so when you subtract, take the product entropy minus the reactant, this is going to be a bigger value than this, and so when we subtract, we get a positive change for delta S. So delta S will be positive for this first process, this first example. All right, so the first step is what we just did with Lucy and Pigpen. We determine whether the reactants or the products has more absolute entropy. Okay, by looking at their states of matter, their complexities, and their molar masses, perhaps. We use the guidelines we just discussed. In step 2, we just say, well, if the products have more entropy than the reactants, and it's actually very useful when you're first doing this to label. So we have reactants going to products. Notice we have a more entropic font. Okay, so we have a smaller s and a larger s. So this is more messy, more entropic, and so that means that the entropy is going from a smaller to a larger value, so it is increasing. Okay, whenever you have an increase in a property, that means that the change in the property is positive. Okay, so in this case, delta S is plus. We don't know the value yet, we haven't calculated it, but we know that the delta S reaction should be positive. The opposite, of course, is also true. If the reactants have more entropy than the products, so we have the messy font going to the neat, more organized font, we have a bigger S. So the messier, the bigger the S, the more organized, the smaller the S. In this case, the entropy is going down, so it's decreasing, getting smaller. And so the change will be little s minus big S, which is going to end up being negative. Okay, so delta S for the reaction will be a negative value. We don't know what yet. Okay, so this is how you basically go about doing this, and you'll do it by looking at the entropies of the reactants and the products and comparing them and seeing if they go up or down. Now there's one more little factor that should be considered with this graph, which looks really confusing at first, okay, but it's actually not. It gives us important information. Notice that we have temperature in Kelvin on the x-axis. We have the absolute entropy, note the strange units, on the y-axis. And this essentially shows us that as the temperature increases, so temperature is increasing from left to right, as the temperature increases, the entropy is going up slightly. Notice it goes up at a fairly low rate. It's a pretty sort of flat rise here. It's going up, but not super fast for solid. And then all of a sudden, when you go from the solid to the liquid state, it shoots up. So that state change makes a difference in the entropy. Now notice what happens as we heat up the liquid. As the temperature of the liquid increases, the entropy changes at a much faster rate. So that's kind of interesting. But even more importantly, look what happens when you change from liquid to gas. There's a gigantic jump in the absolute entropy. So what this tells us is that gas is much, much more entropic than liquid. Okay, so remember we said gas is more than liquid is more than solid. It's not that simple. Gas is much, much more entropic than liquid. Okay, and then liquid's a little more entropic than a solid, not nearly as big of a jump. And so, because of this, if we have any reaction that has molecules of gas anywhere in that reaction, we can just look at the molecules of gas to determine whether delta S will be positive or negative. We can sort of ignore everything else, all the other entropies and what they are, if they're high or low. We can ignore all those if there's gas in the reaction somewhere, because gas is so much more entropic than anything else. Okay, so a good way to estimate delta S, if your reaction has gas, is if the reaction produces more gas molecules than it consumes. Okay, in other words, if there are more product gas molecules than reactant gas molecules, delta S is positive. If the total number of gas molecules goes down, diminishes, then delta S will be negative. This is just boom, you're done. Okay, now here's where it's a little complicated. If there is no net change in the total number of gas molecules, so say you have 2 moles of gas on one side of your reactant side and 2 moles on your product side, then your delta S may be positive or negative. It's hard to know for sure. You have to go, so here you'd have to look more at the other states of matter and molar masses and complexities and all the other stuff we talked about earlier, okay? We do know, however, it will be a small value. Okay, so delta S will be relatively small, relatively close to 0 if there's no change in the number of gas molecules. All right, so let's do a practice problem just to see if you can apply this idea. Okay, which of the following processes have a negative entropy change? In other words, delta S system will be negative. So hopefully you chose B, okay? B is the correct answer, but why is that? Remember that to have a negative delta S system, the disorder has to go down. So we have to have a bigger S on the reactant side and a smaller S on the product side, which means we need to have the number of moles of gas go down. Okay, so if it's got gas, then we can just use the gas. So notice we have a solid and aqueous over here, and a solid and a gas, right? So on this side of equation A, we have 0 moles of gas. Here we have 1 mole. So we automatically can say that this side has greater S. So that must mean that entropy is increasing, which means delta S is positive. Okay. For equation C, very similar. We have a solid going to 1, because there's a 1 in front of the N2O, right? 1, 2, 3 moles of gas. So this clearly has a large positive delta S. There's a lot more disorder over here, so entropy, delta S is going up, is positive. Same thing here, we're going from 2 moles of a liquid to 2 moles of a liquid and a gas. Okay, so in A, C, and D, delta S is actually going up. Only in B is it going down because we have 2 separate moles of oxygen atoms. So there's a 1 here and a 1 here, which is a total of 2 moles of O gas. And over here we have 1 mole of O gas, the 1 in front, okay? And so the number of individual molecules has gone down. Individual molecules of gas has gone down. And so our delta S in this case is going to be negative. And so it's choice B. So in this video, we realized that it was too hard to think about the entire universe when talking about entropy. So we decided to break entropy or disorder down into the system and the surroundings, to think about those separately. We looked at the system first and how to determine or rank the entropy of individual compounds or molecules. And then we looked at how to determine the entropy change of systems or reactions. And we looked particularly at the importance of gases in reactions, how that really rules the entropy of the system or reaction, or rules the entropy change of the system or reaction. So he said, if there's a gas in our reaction, then we can just look at moles of gas and ignore everything else. And we did that qualitatively. So in other words, we just looked at the sign change, whether it was positive or negative. And in class, we're going to look at how to quantitatively calculate the change in entropy, and we'll also look at how to determine the entropy of the surroundings.